computer. Okay, we see the little record button. I'm sharing my screen. I'll close this. So let's look at our calendar really quick. So we finished 3 class sessions. We're on May 15th. We're going to look at import, export, data manipulation today. Just a reminder, I'm going to be out of town on Tuesday, so we have no class at all on Tuesday. So take a nap, do some more lab work. It doesn't matter. Just do whatever you want to do on Tuesday. I will not be connecting with you on Tuesday. And then Thursday of next week, we're going to be back on Zoom together to talk about our visualization. It's always a fun topic. Okay, so this is that. Later on today, we're going to be going over some code. You have 2 options to download the code. You can go to this, get this zip. Go here, download this, and it's everything you need in one folder. If you don't like unzipping folders, then it's a little bit harder. You have to go through and download each one of these things individually. There's 1, 2, 3, 4, 5, 6, 7, plus the R script. So 7 things. Download them one at a time, or download this zip folder and unzip it on your computer. The most important part is this R script. We're going to use that to import some of these tables and do some manipulations. So we're going to talk about it first with the slides. So I said this on Tuesday. If you want to dive deeper into R and things you can do with R, these were some of the tutorials that I found useful. Pick 1 or 2 of them, look at some topics you're interested in, and it's going to go more in depth than I can go into in 3 weeks of a course. Some basics that I just wanted to go over that we've been talking about. Think about your variable types. You know, we have numeric variables, we have character strings, we have booleans. Think about what you need to do with that variable and make sure it's the correct type. We talked about using logic equations with if statements, for loops, while loops. If we want to repeat a process, if we want to have a conditional process, those are there for us, with the warning to never use a single equal sign when we're doing logic, and watch out for infinite loops. We learned how to structure a data object. We had the scalars, which was one thing. We had the vectors, which was multiple things that we put together with that combine function. It was C, and in parentheses, we listed out our scalars. We also had matrices, which were 2-dimensional things, and arrays, which were 3-dimensional things. I don't know if anyone ever uses an array, but they're there for you if you need them. We also learned about lists. Lists give us the most flexibility in a complicated system. If you want to package lots of different objects, you can put them in the list and they'll all be in one variable. And then we talked about at the end of Tuesday that we can use a data frame for the most flexibility because each column is a different sort of measurement, and each measurement could have a different type. We could have numeric measures, we could have categorical measures. And we also talked about how with those categorical measures, we can factor them so that R knows these are the set levels of my category, and this is the order that I want them to go into. I'm going to hide these floating meeting controls. There we go. Now we have all the screen. Okay, I'm right here. Okay, so today we're going to talk all about data frames. We already talked about pre-formatting the data at the end of last lecture, so that we get that over with. Today, I'm going to introduce functions. So if you're following along on the PowerPoint that I have on Carmen, it doesn't have this part. I kind of threw it in. because it kind of makes sense with the flow that we're going with. And I have to condense some of the stuff since we're missing Tuesday. So I'm going to introduce functions because this is an important thing for us to understand when we move into importing data. We use functions to do things in R, and one of the things we're going to do is import data with a function. So that's our second thing. We're going to explore the data, we're going to manipulate the data. So I'm not going to talk about absolutely everything you can do with a data frame, but I'm just going to give you a taste of some of the things that are possible to do and give you an idea of how we handle these kinds of things in R. And then at the end, we're going to talk about exporting our data. We can look at text files. We can put them into comma separated files. We can save them as our data objects. So think about how you want to store your data frame for later. Okay, so now we're going to talk about functions. A function is a block of code that is run whenever it's called. You are able to send data to the function. The function does some code, and then it returns some data. And the technicality of a function is it can only return one thing. So if you have multiple things you want to return, before you send them back, you package them up in a list. Send them back as one object, and then in the rest of your code, you can parse those out, use them as you want to. The cool thing is that once we get more advanced, we can make our own function. So maybe there is a bit of code we wrote to do something. Maybe we're generating a plot. And we know we want to generate this plot multiple times with slightly different parameters, or yeah, we'll call them parameters. It gets tricky on the next slide, but with slightly different things in that plot. Maybe we want to plot a different gene every time, and we want to have a different title for our plot. We can take that code that we've already written to do it once, package it up into a function, and then just call that function anytime we want to generate that plot. It's not very hard once you kind of get the hang of it. I don't personally use a lot of functions, but it is a very powerful thing to do. It's good coding practice. Okay, and packages. We use packages a lot, and all a package is a bunch of functions and information on how to put them together. Now when we load that package, the functions are in our environment, even though we don't see them. And these functions, they make our lives easier. If we want to see the written part of the function that the authors of the package made, we can just type the command, the function, without any parentheses. So this is read.table, and then we hit enter, and it prints out this function. In the next slide, we'll talk about the function. But it's really complicated because it was written by somebody who had to account for all of the different differences that you might encounter when you want to read a table. So they have a lot of things to keep track of. And you can see if the file is missing or there's no text there, then they spit back errors. And so there's all of these different catches of what if something's missing that are built into this function. These are complicated functions. So the super simple function, we have a name. This is my function, and we're assigning this function to that variable name. We let R know we're building a function with the word function and the open and close parentheses. And then everything in the curly brackets is the code that's going to run when we call that function. So every time we call this function, it's going to print, this is my function. Yay. And so if we want to run this function, we would run it with the word my function in open and close parentheses. It's as simple as that. So what are the parts of our function? We have the name of our function. We have the function. And then we have the script to run, which I've already said. Now, this super simple function does not require any input since these regular parentheses, they're empty. But arguments are variables that can be sent into the function and used in that bit of script within our curly brackets. And within these blank parentheses here is where we would define our arguments. And you need to define any arguments you expect to be inputted to use in the function. Let's see what that looks like. Now I have to say something about arguments versus parameters. So an argument is the value you send to the function. A parameter is what is in the parentheses of the function definition. And I will never remember this, but if you're wondering, that's the difference. So we have my function, we're running it, we're saying the parameter in our function is equal to this input that we want to send to the function. And the input is the argument. I will call them arguments or parameters interchangeably. So don't ask me after the slide. Okay, so the point of showing you how functions work is we use functions all the time. We don't really think about it a lot. But if we look at the help information of a function, understanding how that function was set up helps us use the function a little bit. Okay. So now we're going to move into importing. And this is the case of you've collected some kind of data, maybe it's clinical data from your clinical trial, and it has patient information and measurements of this medical issue and outcomes. Is this patient alive? Is this patient deceased? Just any kind of information is in a big file, and you want to pull it into R so you can do things with it. So we have a couple of options. If this is a text file, if it's a CSV, any kind of flat file can be read with this function read.table. If we look at read.table's help page, this is what it gives us. So here's our function read.table. Here are the parameters of this function. At a minimum, we need to give read.table a file. Now we'll see a header. We could let read.table know if the first row of our file should be used as column names. We would set header equal true if that was the case. But by default, it's going to assume there are no column names, and it's going to make column names for you. And then the third most important thing to tell it is the separator. What is your delimiter for your table, your file? Most of the time, we do tabs. So it would be a backslash and a T you would use as your separator. Maybe you had a comma delimited file, you would put a comma there. But by default, the separator is nothing. So you need to tell read.table what to separate your file by. This is a lot like when you open a text file in Excel and you need to tell Excel how to divide up the columns, or everything's going to get squished into one column. Some other important parameters you might want to provide is your table arranged with definite row names that are all unique. Then you would set row names equal to 1, meaning this first column are my row names. And those names would be held in a place for the row names. The other one you might want to set is strings as factors. So when you import your file, do you want R to automatically convert all of your character variables to factors? That might be really good if you have a variable like alive or deceased. That has two levels, and you might use those two levels for statistics or visualization. You might not want your strings to be factors if it's something like the sample ID. Every sample ID is unique, and you're never going to be really grouping by sample ID. You might be, but in your particular case, you don't want to. So you might leave strings as factors as false, and then by hand choose which columns you want to turn into factors. DEC specifies what you're using as decimal place. I think in places like Australia, they use a comma instead of a decimal place. NA strings might be useful, so you can specify what text you want to use as a missing value. Now, most of the time, we expect the missing value to be NA. Sometimes you might have the word unknown for a missing value, and you want to specify that as you read in your table, and it will convert any unknown to NA. Just makes cleaning up your table easier. Some useful reminders when you run this read.table function, your path and file name needs to be in quotes because this is a character string. You'll need to use a full path unless you've set your working directory and your file is present in that working directory. We've already talked about the headers. It's true if you want to use column names, false if you want R to make up column names for you. Sep is your delimiter. Now there are some variants of read.table with set values for some of these parameters. There's read.csv where you don't have to specify that your delimiter is a CSV, is a comma. The read.csv has it as default delimiter as a comma. Let's see, if you want to import a CSV with commas for decimals and semicolons as delimiters, then there's read.csv too. If you want a tab delimited file imported, you can use read.delim instead of read.table, where you don't have to specify the delimiter as a tab. Okay, now dates will be automatically imported as characters. If dates are important to the analysis of your data, you might want to format them as dates. And here's an example where we format this table $, comma. We are setting it as a date, and we're specifying what format that we want to use. How is this date named? Or if you're running into trouble a lot with this, check out the package Lubridate, which has functions specifically for handling dates. Sometimes you might get some import errors. Errors of cannot open the connection or no such file means R cannot find your file. Maybe you're using the wrong path, you're using the wrong file name, you've misspelled it somehow. You don't have the right suffix. There's something where R cannot find your file. If you forget to include header equals true, all of your column names will be something generic, V1, V2, V3, and your what should be your column names are going to be measures in your table. Also, R might mishandle your numeric columns and store them as a character string. So we import a table, we always look at it, we can check what types of data are present with that str, check our dimensions, just check to make sure what you expect to import actually imported. There's some other options for reading files in. I don't use these, but there's some other packages. There's read.table as a package, readr as a package. The thing about readr is it's from the tidyverse universe. And when it reads in a table, it reads it into this special format called a tibble. It's a tidyverse table, and it's sort of like a data frame, but it's different. It's in its own format. It's in its own world because it's the tidyverse. So if you use tidyverse packages and functions, just be aware that your tables might be tibbles and you need to handle them a little bit differently. If you're importing enormous tables, check out the packages FF and Big Memory. I've never used those either, but they are options. Okay, so we in the script part of our class, we're going to go through some examples of how to use these functions. So I'm not going to leave you with no examples. But next, we're going to talk about exploring the data. We've imported the data, we've checked it out, made sure it imported okay, and now we can do things with it. Viewing the table. Just click the table name in the environment. It will pop up. You can look at it. It is possible to print the table into the console if you just type the name, but I don't recommend doing that because if it's a really long table, it's going to be scrolling for a long time. So it's best to look at your table just by clicking on it in the environment. We can check out the data types with str. We learned yesterday that means structure. It's compact, it's informative. You can copy and paste and comment for later. I think if you want to just copy it into your code and then you can comment it out. And I'll show how to comment out things in the script part. But that's a little note for yourself, for anyone else using your code. This is what you should get in. We can print out the call names. So this is a function called call names. It works in our table name, and it prints out all of the column names on our table. If you did this and they were all V's and a number, you would know your column names didn't get imported correctly. Now we've seen this notation a lot. I've talked about our table name, $ column name, and that's how we can refer to a specific column by name in our data frame. We can use this to, for example, ask for a table of this column. So it's going to go through every value in this column and count how many times that value happens. It's a way of summarizing our data. You can do it on one column as our first example, or you can make a 2x2 table where the rows, I'm thinking, are going to be the values in column name A, and the columns in our 2x2 table will be the values in column name B. And then the values in our table is how many times that particular combination of A and B are seen together. We can pull out the value of any one column and save it into a vector. If you want to do that, then you will have a vector of just age. Maybe you need to do that to send age to another function or something. But when it's in a vector, it's kind of easier to do math on it because you only have to type AGE. You can get your average. You can get a summary, which is going to show you the range of this variable, the average, the median, the interquartile range. A lot of information you can get with a summary. But you can also do the same thing directly with this table $ column notation. If you don't really need to create a new variable, you don't have to. We can apply functions directly to a column. And the nice thing about summary is, so here we're just doing summary on one column. You can do summary on the whole table. And for any numeric variables it's going to tell you that range information. But for any categorical variables, if you factored them, it's going to give you the equivalent thing that the table function would give you. It will tell you what are the possible values in this column and how many times did we see those possible values. So summary is very powerful too. Table and summary I use more than anything, it seems like. Okay. We talked about indexes a little bit last Tuesday with a matrix. We can do the same thing with a data frame. We have this data frame name and then square brackets. We can refer to the row and column by number. It's a little tedious, but we can pull out the 747th row and the 9th column. Another way we could do it is if we knew the 9th column name was Neoplasm Disease Stage American Joint Committee on Cancer Code, we could specify that column directly with our column notation. And then in the square brackets, just give it the row name. So you can do it either way. Columns, we get the special $sign notation. Rows, we don't really. So rows, I think it's more useful to pull it out with an index. We can sub-select based on indexes if we wanted rows 1 through 10, columns 4 through 25. We can do that with this index notation. If we wanted to be more choosy and we wanted rows 1, 3, and 5, then we would provide that as a vector with our C combine parentheses notation. Sometimes you just want all of the rows from some of your columns. Let's see. The first example is all columns from the first 8 rows. So in the column, in the row part, the part before the comma, we tell it keep rows 1 through 8. The alternative, maybe we want all rows from the first 8 columns. We leave the rows blank because we just want all of them. And then after the comma, we tell it we want columns 1 through 8. We can remove rows or columns with this minus sign. It will remove whatever rows or columns you specify. Down here, we can also refer to columns by name with this square bracket set up where we leave our row value blank, we have our comma, and then we have our vector of column names, A, B, and C, in our combine setup. This last comma should not be there. R would complain about that. So, okay. And then one more tip about indexes. You can filter indexes based on logic. Maybe you want to pull out every row where the age is greater than 50. So we have our table name, and inside the square brackets, in the row side, we're asking, pull out the diagnosis age greater than 50. And then we'll save it back out to this subset table. And what this does is for every row in our table, it's going to ask a logic test. It's going to say for row 1, is the diagnosis age greater than 50? True or false? Row 2. And then this is going to return a bunch of vectors of trues and falses. And it's going to pull out the rows where this logic statement is true. And that's what gets saved out as the subset table. Alternatively, it's much easier to use the subset command. And I never do it like this. It's hard for me to think this way, but I can use the subset function. I can say subset my clinical table comma, where this table $ column is greater than 50. We don't have to specify the table, so the second line of code is exactly the same thing because R knows, look in this table for this column name and use this logic. We can make really complicated logic statements. So in this last subset function, we're pulling from our table. We want diagnosis age to be greater than 80 and the overall survival status to be living, and pull out from our table, get columns patient ID, diagnosis age, and overall survival status. So those will be the only 3 columns that we keep. And that gets saved into subset table 4 because we want a smaller subset of our data to do some sort of analysis with. Sometimes you might need to sort a data frame that maybe you want to select the top 5 or 10 data points with the highest value. We can do that. We have examples in the R code for later. Okay, well, I'll show that later. Here's some fancy sorting options where we use order. We tell it order the columns based on block 1 and block 2. If we want to reverse order, so here we are reverse ordering measure 1 and we put a minus sign in front of it. It's that easy. So it will sort on 2 different column names, but it will make the second descending. If you have a complicated setup and one's a character, apparently you can force it to be used as a factor with this XTFRM function. And it will probably put it alphabetical if you don't specify anything different. But okay. Now we've talked a little bit about factors, and factored characters are very useful, but they're going to factor your variable alphabetically by default. Sometimes that is not useful. Like if you have a tumor normal situation, it's going to put normal first, and the normal will be on the positive side. But if we want to switch it around to make more sense with what we expect the change to look like, we would want to set the tumor as our main group and the normal as our secondary group. That's one case where that's important to do. So maybe you have a variable that has values low, medium, and high. If we didn't specify the levels, this would be alphabetical, and it would go high, low, medium, I think. And that would not plot very well. If we wanted to have these 3 groups, we want it to make more sense. So we're factoring this table $ comma column, and we're setting the levels to be a vector in this order. And then in this next command, after I factored it, I'm going to order my table based on this value 1. So it's going to go all of our low records, then our medium records, and then our high records saved into the same table we're working with. Okay. So now we're going to talk about adding columns, adding rows, adding to our table that we already have. There's a function called cbind, but I'm going to warn you to try not to use cbind because it assumes that the rows in your 2 things are in the same order that you expect them to be in. Be very careful if you want to combine 2 tables using cbind. We're going to talk later about the merge function, and that is a much safer way to go. We can also make a new column with that table $ column notation. me have, no, I don't have an example. Okay, I have examples in the scripts, but I think I did one on Tuesday where we can have our table $ new column be assigned as combination of some old columns, or maybe we do some math to the old columns and then we save it in that new column. So we can remove columns. So I showed this a couple of slides earlier. We can remove columns based on their numerical index. We add in a subtraction at the beginning of that vector. We can also have ranges. So this is 1 through 5 rather than 1, 3, and 5. If you have a small number of columns that you want to remove completely, you can specify them by name. Here we are setting column 1 to be null, and that means that it's going to be deleted from our table. Adding rows is a little bit easier than adding columns. If we have table 1 and table 2, they have exactly the same column names. R will check. Then you can just R bind or row bind one table to the other and save it as a new table. You could even save it and write over table 1 if you wanted to. So I use this sometimes if I want to use a for loop and run this analysis over and over and over again. I keep a running table of all of my results by R binding the result that I just generated back to all results. So here we create all results as an empty table. We run result 1. We append, we R bind result 1 with all results and save it as all results. Then we run the analysis over again. With our second analysis, we get some values and we R bind results 2 to all results and save it as all results. And all results will now have 2 records, one record for result 1 and one for result 2. Maybe you had to do this 10,000 times and it will run pretty quickly. We can remove rows with this index notation, or we can subset. Subsetting makes more sense. We can refer to columns by name and use different ranges. So subset is your friend. Now, I warned you a couple of slides ago, you can use cbind to combine 2 tables, but that is only if they have the same row order and you are sure that they have the same row order. A safer option is merging. This is when you want to combine one data frame with another data frame, and you know they match up by one row. You will specify, they will match up by one column. The column name in one data set will mostly equal the column names in another data set. And I'll show an example later, but they're going to try to match up based on one particular column. We specify the column name of the tables that we're going to match on. If you're trying to match on row names, then you specify 0. And I'll show examples later. dplyr has a merge alternative. It's from the tidyverse. So if you merge with dplyr, it's going to return a tibble. Now it's pretty easy. If you do get a tibble and you're having a hard time managing it, you can convert a tibble to a data frame. So be aware of that if you get into the tidyverse and really like using those commands. You can go back and forth from tibbles to data frames. Okay, and then something else I'm going to talk about in our coding part later on is reshaping data frame formats. I get my example from this link. Sometimes our data set is in a square format. That's what we're most used to seeing, where each row is a different patient and each column is a measure for that patient. Now, sometimes it makes more sense to put our data in a long format where we have sample one height is something, sample one weight is something, and the height and the weight are on different rows. So sample one is going to be listed over and over and over again for every measurement. And then we go to sample two, has like 5 measurements. So that's the long list. And there are functions in R to switch from one format to the other and back and forth. We talked a little bit already about the summary function. It's very useful. It's very basic though. It's not going to be something pretty enough to publish. So it's just informational for you. If you want to get a summary of your data in a publishable format, check out the GT summary package. It's pretty easy to use, and the table_summary function will summarize whatever columns you want. It will even group them for you. If you have 2 different cohorts, you want to summarize all of your clinical information and check to see if your cohorts are statistically different or not. Table summary will calculate those statistics for you. It's powerful. And you can export it into a Word document and change the formatting and then put it in your manuscript. Okay. So we've talked about what a function is. We've talked about importing data frames. And I've shown a bunch of different examples of how you can check your data frame, manipulate your data frame, do things to your data frame. And now you've done your analysis, you've saved your results, and how are you going to take that information out of R to save it forever? You need to export your data. There's some options for doing this. So just like we had read table, we have write table. It's a function that will write a data frame to a file that you specify. You would tell it the file name, possibly the path, if you don't want it in your working directory. Tell it what you want to delimit it with. A tab or a comma is most common. Do you want to export your row names, and do you want to export your column names? Sometimes if you've made those row names to be something important, you want to export those row names out with your table. Column names, the same thing. If I assume your column names are something informative and useful, and you want your column names to get printed out into your file too. If you have row names and column names that you want to export, you need to set the call names argument to be equal to NA, because this is going to hold a place at the beginning of our column line. It will hold an empty slot for your row names. It took me a long time to figure this out, and I would export my text file and all of my column names would be shifted to the left, and I just have to put that tab in to shift them back over until I realized I was exporting wrong. So I'm telling you this now so you don't have to go through years of exporting wrong. And we'll go through some examples so you can see what happens when you don't remember to set your call names to NA. If you want to write to a CSV, you can do that. You can do that with this function. You can do it with write.table, specify the delimiter to be a column, or you can use write.csv, and you don't have to specify because it prints a CSV by default. It also prints call names by default. So that might be a useful shortcut. There's other options. The package read.table has fwrite. The package read R has write TSV, write CSV, and write Excel CSV. But I read Do not ever write directly to Excel. It will cause problems. So be careful. Okay, another option is to save an object or multiple objects or your entire environment to a .r data object. This is the R saved object file type. I don't know. There's probably a better way to say that. But this is a format of exported data that is formatted for R. Here we have examples where you can save one object, just our data one table. You can save multiple objects. These can be tables, lists, any type of object you generate in R. You can save all of everything in your environment. And then sometime later, maybe in a different script, you could load that data in again. We load this file. Maybe you need to include the path to your file if it's not in your working directory. There are other options for saving our objects in probably a more space-saving way. I know for single cell, we use the Q save a lot, and I'd have to look up what the package was that we installed to use Q save. But a word of warning I'll give you, for our data objects, they don't hold up well across years and years. So you make an R data object today, and 5, 10 years down the road, R has been improved so much that it won't even recognize old R data objects. So that's a problem. I think the Q save is a little safer. So I had a group in 5730. They wanted to download some public data that was in our data objects, and they downloaded it and they found they could not open it at all because it was so old. And I went and I did some searching and I found some updated our data objects for them, and they were able to do that, and so they could actually do what they proposed to do in their final project. And they were very happy. And they also learned a lesson that our data objects, they're okay for right now, but if you want to save data forever, put it in a text file, put it in some other format that will be safer. Okay, so what did we learn? Think about your data file before you import it into R. Is it cleaned up? Are the column names informative and short? Are there NAs where there might have been blank spaces before? How are we going to import our data? What options, what arguments do we need to include in our read.table function? Did the table get imported correctly? Are the variable types correct? What did the summary tell us? Which columns need to be factored? What do we need to do to modify our table to get it into the format that we want to use it? Do we need to merge some tables together? Do we need to filter it, subset it, do some transformations? Maybe we need to log transform all of the numerical variables, change the data shape so it's better for plotting. What do we need to do to analyze our data to format it correctly? And once we have something to save, how are we going to export that information? Are we going to export to tab delimited files, CSV delimited files? Do we want to put big R objects into a file together to make it easier to import into R tomorrow or next week? So think about the data that we're using from head to tail. Okay, so looking ahead to next week, we're going to continue next Thursday talking about R, talking about visualization. I'll remind you, we will not have class on Tuesday because I'm going to be in California giving a poster session at this time. So I'll get an email if anyone logs into Zoom. but I'm not going to be here. So we're going to talk about visualization on Thursday. Okay, so we've talked a lot. Hope everyone's awake. And now we're going to get the scripts. I'm going to download this zip package. I'm going to extract it. I've already extracted it. Okay, there we go. If you want to follow along with me, you can. Okay, we're going to start easy. I'm going to do this. Okay. So yours does not have any path at all. So let's start out. Let's make some space, and then we're going to set our working directory because this isn't even right for me right now. This is not where I'm working. So I'm in the downloads folder. So we're going to do this. I go to session, set working directory, choose directory. Okay, I'm right here. I'm in D downloads 4R import export package. Okay, and that's set our working directory. Maybe we want to save it. I went over to history and I sent it to my source. I save it. Okay, so we can run that. Run one line. I'm going to copy this path and I put it in the quotes that we have here. So we're running the read table function and we're telling it our file is this string. The example I'm using has single quotes, but it works the same with double quotes as long as it's consistent on either side. This is the way to import the text file with a full path. Maybe your text file is not in your working directory. You want to say get it from that folder over there. So maybe you want to specify the full path. We're saying we do have a header. So header equals true. The delimiter is a tab. And please convert any strings into factors. So we're going to run this one line, go back to our environment, and move this. Okay, so we see we have a table right here. It has 1,000 observations. These are rows. It has 13 columns. I could type this name into the console and we'd be sitting here for 5 minutes while 1,000 observations stream by. But we're going to open it and look at it. So this is TCGA, breast cancer, clinical table. These are our patient IDs. There's age, there's gender, there's information about ethnicity, there's cancer, when their cancer is diagnosed, there's copy number, I think, mutation count, their disease stage, their survival time, whether they're alive or deceased, and if they have, how long have they been disease-free, and whether they have recurred or progressed. So that's the information in our file. If we were to run this like this, it's going to, it actually worked. Okay, because I do have it there. You're going to get an error because you do not have this folder. You don't have my folder on my computer. So you're going to get an error. So what you want to do is run this instead. There. This is setting the working directory that I assume you just set up. You run that, and then you import because it's in your folder. Now, okay, so I have a space here. We don't have to type this whole command because RStudio has this button over here to import a data set. We click that, we say read it from text. We go to our computer, we can move around, it's just Windows we can say, open this TXT file. And this is our TXT file. We can tell it whether we have headers. So these are going to be our column names. If we didn't, there would be V's here. So we definitely want column names. If we wanted to set the patient ID to our row names, we could do that here. I don't know if any of them are replicated, but we might find out. We tell it what is our separator. It's a tab. And we tell it what our decimal place is, whether there's quotes around the character strings. There's none. Okay, and then if there was a commented out line at the beginning of this table, we could tell it that, and it would skip that line and go straight to the actual data, but there's none. And here we can list what other values for missing we might want to include. Just NA is good. You click this box if you want strings as factors. We're not going to do that. Okay, then we say import. Oh, I got an error. So some of those sample names were replicated, so we can't have them as row names. We're going to do this again. Okay, we have headers, yes. Our row names are just going to be automatic. We cannot use the first column. Everything else is the same. We import, and it pops it up for us there. And you can see this command down here, it built up that command for us. So we can go to our history. Might have to scroll down. And this is the command we built. We're going to send it to this location in our source. Now, by default, it sets it up with the full path. Full path's always safe, so it's fine to leave it in. If you want a shorter line, then you could delete that, but it's okay to leave it. I also gave you the data in Excel format. This is an Excel file, purely Excel. The nice thing is we can import Excel files from Excel through this import button. It looks a little bit different. We're going to choose this Excel file, opens it for us. It lets you change any variable types. Like if there was one that was wrong here, maybe you want year to be a character, then you could do that. And it's going to change this command. This is our code preview that it's building up for us. It's reading in Excel. This is our file name. It's set the column types. Since I changed that one, it's specifying it for everything. Let's change it back. I don't know if it will break anything. Okay. So if you make any change, it's going to incorporate that into our command down here. We can set the table name, which sheet we want to pull from, row names, first row as columns. Okay. Yeah, we can import. So we have the same table here, but it came from Excel this time. And if we want to copy and paste, we could get it right here, or we can go to history. What we need is the package that was used to read this Excel and also all of this, the command. We're going to send that to source. This is all on different lines, but that's okay. R knows to go to the next line and keep reading. Let's see if we can format it a little bit nicer. Indent lines. There we go. So I went to code and re-indent lines, and it set up the indentation so it looks nicer. As we do this, you might notice when you hover over things, it's not doing it for me again. You hover, it's proving me wrong. Okay, sometimes when you hover, it pops up that function for you. You can see what options you need to specify, what options are optional. how you would set up a command to do this. It also does this as we're typing. Let's see if we do read. So it gives us, these are all of the functions that start with read. We can pick one of them. We can keep typing, read Excel. And then it pops up this help. We could say path equals this and whatever. R helps you out a lot. Okay, I'm not going to talk about that. Okay, here's some alternative import commands. We can use read delem, where we do not have to specify that the separator is a tab. And we have read CSV. There's a CSV file for you to do that. Okay, so let's look at our data. We do a str. Whoa, there's a lot. So for, oh, it's a tibble. Oh no, because I imported in Excel, it is now a tibble. I'm going to say as data frame this. There we go. Now it's not a tibble. There we go. Now it's a data frame, has 103 observations or rows and 13 columns. Here are every column. Our age is numeric. Our year is numeric. Oh, CNA is a character, which it seems like it should be a number. So is mutation count. So that might be some that we could change. CNA as numeric. CNA, it's going to complain. I know. Yeah. CNA. Yeah. So there's some NAs. Those were just missing values, and it turned them into NAs. So that's good. That's fine. If we look at our STR again, so CNA is now a number. We could do the same thing with mutation count and with these overall survival months and disease-free months. Those, they have NAs in them, and it's just not being treated correctly. Okay, we can get our column names, which we've seen already. We can print out a column. There are a lot of, so it's printing out 1,000 things here. It's not very useful. But if we do table of our table $ column, this is the table function. Then it will show us how many records had stage 1, how many records had stage 1A. So if I say, get a table of neoplasm disease stage, then this is what you would do to that column. I know I also call this clinical table a table, but if we table a column name, then I'm looking for more of a summary of it. We do that. Then this next example has both disease stage and survival status. So we can see, is there a difference in deceased or living across survival stages? So like stage 3A seems to have a lot of living patients. So there's statistical tests we could do to ask, do deceased or living individuals, are they more, do they have worse stages or better stages? Okay, so I'm going to show you how to do autocomplete with tabs and menus after doing this. Okay, so we're going to do table. I'm going to start typing the table name. We only have one table name. It's TCG. I'm going to tab. I don't even have to tab. It pops up. It says, this is one of your environment variables. Do you want to use it? And I hit tab and it fills it in for me. And then I do $, and it automatically pops up with all of those columns. I can go up and down, or I can start typing neo, and it pulls up what it thinks I'm typing, and I hit tab. And then I do it again. I do TC tab. Yeah, I get that. I do this. What am I want to pick this time? Mutation. I don't know how that's going to work. What do I pick? I did overall survival. Okay. Overall survival status, and I get the same thing. So use tabs and options to your benefit. Okay, we did this. We saw this in class. We can save a variable outside of our table, just age. It's now a vector. And we can get the average age, a summary of age, which gives us the minimum, maximum, the median and mean, and the first quartile and third quartile. So that's going to be like the box of your box plot. But we can also do the same thing directly on this table $ column. So we don't have to make a new variable. Let's see. Diagnosis age. There. If we do summary on the whole table, we will get that numerical information. And so this doesn't look so great because our character variables are not factors. So let's go up here. I'm going to import, okay, I'm going to run this command. We ran some different ones where it was not set, but this command sets strings as factors to true. We run it again. One of the other imports we ran did not do that, so it doesn't look so nice. And we're going to run this summary again. So here, for disease, here, overall survival status, deceased 216, living 787. We could get that same information if we tabled. Status. Run that, and we get the same thing. We have some examples where we're pulling things out based on index. You can run through these, make sure they make sense. So here we're subsetting the logical index where it's asking for each row, is this logic statement true or false? It's going to return back a vector of trues and falses, and then save any row where this vector has a true value. So here we run this, just this command right here, and there's that true-false vector. We put the true-false vector in our row space of our index, and we're able to subset the table where age is greater than 50. Here's some more complicated examples where we use ors and ands. Do we want to pull out based on more than one column? You can do that. But if you're going to be doing this, use subset. It's easier. It makes more sense, I think. So let's do this third one, where we're going to subset our table where age is greater than 80 and overall survival status is living. It's in subset table 3. We have 30 records where the age is old and the person's still alive. If we wanted to pull out just the unique patient IDs, we've added on a select option inside of our subset function. We're saying pull out the patient ID. And then also I've put another function around all of this called unique. And with all of these patient IDs we get back, I want to just keep the unique ones. So let's see if we get 33 or not. Yeah, we still get 33. So apparently all of these records, all of these patient IDs are unique. Okay. We have some examples of sorting. I'm not going to go over these. We have some examples of adding columns. So this one, I'm going to talk about this example where we are looking at median at diagnosis age, and I want to pull out what is the median of our diagnosis age. So we run this and we save it to a value called med. It's over here. Apparently, median age is 58. We're using an if-else statement. So this function, it says you have a test, then you tell it what to do if this logic statement is true, do this, and also provide it with what to do if this logic statement is false. And what we're going to do is we're going to save the results of this function to a new column called age split. So what are we looking at here? So wherever age is greater than the median, we're going to set it to the value of high. So if this is true, it's going to get the value high. If this is false, it's going to be assigned low. So let's do one thing. I'm just copying this. I'm doing table and this logic statement. If we do a table of a logic statement, anytime that logic is true, it's going to be a 1. Anytime it's false, it's going to be, oh, it's just false and true. If we do a sum, that's the other thing. If we do a sum of a logic statement, trues are 1 and falses are 0. So we see 526 patients have an age above the median. We sum our logic statement and we see that 526. Maybe you have an instance where you want to ask how many of my records are greater than this value or less than this value. You have some logic statement. You can use that sum of a vector of true falses to pull out that number. Okay, so we're going to run this line and we're going to do a table of our age split. And we see 477, the value is false and they're assigned low. 526, the value was true and it was assigned high. And if we look at our table, we saved it to our original table. It is right here, our age split. So maybe we could do survival analysis later on in the class. We could say, does having a high or low age, does it lead to earlier or later death because these patients have cancer? Okay. We can factor a column and save it as a new column. Let's see, we can do math to a column and save it as a new column. So here I'm taking age and I'm adding 10 to it. So now in our table, we have age plus 10. That's kind of silly to have age plus 10. So I regret that decision. So I am going to remove this age plus 10 column by setting it to null. Okay, we didn't make this up here because I didn't run the code. So if we run that, it will be fine, but it's not really doing anything. Here are some examples. Okay, so I'm going to split my data set. I'm subsetting our table to where the age is high, and I'm subsetting it so that the age is low. So we have 2 different tables now. We can check out the summary of the age. And since these tables, they have the same columns. They both have different information. I think they're these. Yeah. So it's 2 different data sets now, but they have all the same columns. So we can R bind them and it's going to be okay. So we put them back together into, this is the remade one, and it has 1,003 records again. And it has the entire range of age. Let's see. Okay, so we're going to skip that part right here, but we're going to talk next about a merging example. I'm going to clean out my environment. Okay. We might not have time to get to exporting, but we'll talk about it in our next class session. I'm going to import 2 files. merge example 1 and merge example 2. We can look at them. So this is a data set. It has 6 patients. It has age and measure 1. This is a second data set. It has some of the same patients, but 2 different measures. So what we want to do is combine the 2 tables into one data set where the name is equal. Now, we're going to use this merge function. We're going to say merge our 2 tables and save it back into both. We're not including any other information. And what it's going to do is it's going to look for columns that have the same name. And that's what it's going to match for if we don't specify anything. So it looks here, and by default, it's matching based on name. If both tables didn't have the word name in it, then you would need to specify my first table, the column I want to choose is name. The second table, by .y, the column I want to use is name. In this example, we don't have to specify because that's the one column that has the same actual column name. So we run that, it's the same. But what you notice is it only has 5 records in it because it's only merging when the name is exactly the same. And apparently there's 5 samples that are in both. If you want to keep any record, regardless of whether it matches the other table, we would set all equals true. That's what I have down here. And it would save all of them. Now we have 8 records. But if we look, sample 6 and 7 do not have age or measure, and sample 9 does not have measure 2 or measure 3. So there's just some missing information there. Maybe we want to keep all the records from merge example 1 and any record from our example 2 that matches. That's where we would add a .x. So it's saying keep everything from X and then see if anything from Y matches. We run that. And so there's just one record now that has some missing information. If we set the row names to be this name, you can see there's no name anymore. So what we need to do, instead of, I'm going to copy this down here. Instead of name, we're going to set this to 0. That's just the handy way of saying match based on the row name. And to make it really clear, you can have both of those, X and Y by, or since both tables have the row names and we want to match on row names, we can just say by equals 0. And we get this table. Now, when we merge on row names, our row names get added to this column called row names. And that's a little annoying. So I just do this because I know it. What we do is we have our row names be row names. We run that. We can see our row names got spit out to our row names. This is confusing, I know. And then we set this row names column to be null, and that will delete it. There is a clever one-liner for merging your table, popping out the row names, and then setting the row names to null, but I'd have to look it up every time, and it's just faster to type 3 lines than to look it up. So this is our merge table, merged on row names, and cleaned up. Okay, this is probably the last thing I'm going to talk about is converting long list to wide list and wide list to long list because it's kind of convoluted. But next Thursday, we will catch back up and real quickly talk about printing tables. It's not that difficult to print out a table. Okay, I'm going to clear this out again. Okay, so here we are talking about reshaping data frames. I am making a data frame that has 4 different values. There's a subject, sex, condition, and measurement. And this format just builds the data frame for us. Okay, let's take a look at it. It's called long data. So you can see our subject is repeated. Can we make the subject be row names in this table? If you see this pound sign or this hashtag, it means the code is commented out. So it will not be run. I'm going to take out the comment and I'm going to run it. I'm trying to set the row names for a long data to be subject. And we get an error because we knew that would happen. You cannot have non-unique values in your row names. But if we had a wide data, I set this up into a data frame. We look at this. Oh, I don't know why it's a wide data 1. Okay, so it's wide data 1. You'll have to change that. Now we can make subject of wide data 1 be the row names, and we do not get a complaint. So here we have row names. Now, if you are running through this code, you're probably going to need to install this R reshape 2 package. Take the pound sign away, run this line, and then comment it back out again. And then you can load this reshape library. I get a complaint because my R version is old. It's fine. Okay, so we're going to take wide data to long data using a function from the reshape 2 package. We look at our, I don't have a wide data. Okay, we look at wide data 1. I'll upload the script to Carmen because apparently I changed these variable names. Okay, so we're going to use melt. Melt. The help is not very useful because it says we give it a table and then we pass further arguments. So in this case, we go to Google, we find someone who demonstrates how to use the melt function, or we look at this example. Okay, so we know our data is wide data 1. We need ID variables. These are going to be the variables that are fixed, that we don't need to have columns for. They're sort of our grouping variables. They're going to be subject and sex in this condition. What are we working on? We're working on wide data. Okay. And then our numerical variables, our measured variables are control, condition 1, and condition 2. We want to set up with a variable name condition. And we want the value that we use to be called measurement. So I've already run this. No, I haven't. Okay, I'm going to run it. I'm going to print it. So now I have my long data frame. It now has a repeated subject and repeated sex. And then our condition is one of 3 variables, and it has our measurement. So it's taken the wide data. We keep these first 2 columns fixed, and it's squished up the control, condition 1 and condition 2 into separate listings. Because this long format, there's some visualization approaches that will work better with a long format. And there's some data analysis techniques that'll work better with a wide format. So going from one to another is useful. If we're going the other way around, we use decast. And I bet the user thing is just as useless. Yeah. So Decast, you get a table, you have a formula. That's useful information. And value variable. Yes, so that's the three things we have here. Our data table is long data. Our formula, so we look at long data. We're keeping subject and sex as our grouping columns. And then we're splitting out condition into three different columns. So subject plus sex twiddled on condition. And then the value variable is measurement. So that's what's going to fill in our square table. Decast, look at my wide data frame, and it's done exactly what we've hoped it would. Now, this is saying make a factor and set levels for, okay, so we're going to take our long data set. Let's see. Is this? No. We're using my wide data set. And we're going to make, I've forgotten what I'm supposed to be doing here. Okay. Factor, my wide, subject. I don't know what I meant to talk about here. Because control condition 1 and condition 2 are numeric, but and we could set levels. C, what are they? A, we have a D, C, B, A. And then let's summarize this. Okay, and now subject is a factor, and you can see the order, I flipped it around. Okay. Let's see, these are just some extra things. Let me see if anything is useful. I've already removed this. We've already talked about these things. Okay, here is that GT summary. We have 3 more minutes. If you don't have GT summary and you want to run through this section, I do include the install packages function for you. And here's the website, which has really nice tutorials. So we're taking our table and we're piping it into this table summary function. This is a special, I think it's a tidyverse thing, but it's a special character that says, take this object, our clinical table, and feed it in to this function. And this function specifically needs it to work that way. So we feed it in, and I know it's going to be, yeah. So this is not very useful because it's including patient ID. Let's do this third one, where we tell it missing text equals missing in parentheses. So it popped up over here in viewer. Let's look at it. Okay, so it's like a text. For 1003 records, our average diagnosis age was 58. Here are the number of records that were female, the number of records that were male. There's the ethnicity. There are 163 that are blank, and some that are not evaluated, and some that were unknown. If I were to import this table again, I would set these characters to be our NA values. Let R know, treat these as NAs. That would really clean up our data. So we scroll through, there's all of this information. It's presented very nicely. We can see down here below for the numeric variables, it's telling us the median and the interquartile range. So overall survival in months the median's 22. The upper lower bound of that box plot is 12 and 45. Let's close this. Okay, that's all I'm going to do today. So let me have a comment. Yes, I'll put the videos up on Carmen. If you want to watch videos after this class is over, I can give you links to an older recording I have of the class on YouTube. I think they're all up on YouTube too. Yeah. Okay, I'm going to stop recording. Remember the